So you guys have done a bunch of stuff with parallel fields and incorporating some work and energy and that type of stuff into parallel fields that you guys start in grade 11. Now we're going to start looking at some point charge electric fields. And this is a little bit different than the parallel stuff, but is actually heavily similar to the gravitational stuff. So doing the gravity stuff first actually makes this an awful lot easier. So it's actually really similar in lots of different ways from gravity. So we're going to actually start with some gravity type stuff. So suppose you have you got a mass, and of course you got the gravitational field going around it. And what you guys did is you guys calculated gravitational fields and looked like gm over r squared to calculate how strong the gravitational fields would be around the mass. Well, an electric field is pretty much the exact same idea. So, you have a charge, you've got a charge, some kind of Q of some kind. And of course, the electric field is going all around it. And it's really the exact same type of calculation and the exact same thing as when you guys did gravity. We just need to change out the values that are actually important. So, for example, for gravity, you guys really focused on mass because, of course, gravity comes from mass and interacts with mass. Well, we don't want to work with mass, we want to work with charge. So we're going to take that and change that to a Q. The R actually stays the same. I mean, in gravitational fields go out in 3 dimensions, make the shape of a sphere, blah, blah, blah. Well, same thing for electric fields. That's the exact same idea. Like, there's really no difference. And the only thing that's left is the constant. So what we need to do is we need to switch this out for a different constant, and the constant is a lowercase k. That's what's used for electric fields. And we'll get to that more of that in just a second. So if we switch these out for the electrical quantities instead of the gravitational ones, this is how we will be able to calculate the electric field from a point charge, very similar to the way that you guys calculated gravitational fields from point masses. So if we sort of put this all together, we get electric fields is equal to kq over r squared, and that is how we can calculate the electric field from any point charge we want. Electron, proton, nucleus, it doesn't make any difference. Okay, so again, it's very similar to gravitational calculations, and that's why I like to start with them first. It just makes this an awful lot easier. Now, the K constant for electric fields is actually equal to 1 over 4 pi epsilon naught. Okay, which seems kind of weird. You got the 1 over 4 pi epsilon naught is permittivity of free space. It gets all fancy schmancy, and that value will actually be in your super sheet somewhere. But the thing is, when you actually break down and you actually put the values in, this actually crashes down to 9 times 10 to the 9, which is one of the easiest constants to remember for this type of stuff. So you can do the 1 over 4 pi epsilon naught if you want, but most people just remember it as k is equal to 9 times 10 to the 9. And that's what goes out in front of the formula in order to calculate the electric field from whatever charge you want. Okay, so let's just take something really simple and make something up. Let's suppose this is a 0.85 Coulomb charge, and over here, let's say you are 1.7 centimeters away from it. What would the electric field be at that location? Well, it's really straightforward, actually. Electric fields, that's kq over r squared. So that's 9 times 10 to the 9. You've got the q, that is your 0.85. You divide that by the radius. Just make sure you square it and make sure you convert that to meters, and you'll have the electric field from the object. So if we do that, we should get like 2.64 times 10 to the 13 newtons per coulomb. And this is, well, it doesn't actually say if it's positive or negative charge. If it was a positive charge, of course, the electric field would be going away. If it was a negative charge, it'd be going towards it. And in fact, if you actually did the calculation with a negative Q, so if that Q was negative and you did the calculation, the electric field would end up being negative as well. But all that really tells you is that it's a negative charge and the field goes towards it. So I typically don't incorporate the negatives with this. In fact, I pretty much never incorporate the negatives in with this type of thing. I'd rather just say that the field's going towards or away or left, right, up, down, because it actually tells me which way the field is actually going. Okay, so this is the basic way to calculate electric fields. Now, one of the key differences between gravitational fields and electric fields is generally with gravitational fields, things are like a star or a moon or a planet, whatever, something generally isolated in space. For this type of stuff with electric fields, it's really common to have multiple charges relatively close together, so we can do combinations of fields, which isn't actually that hard to do. You just got to find the fields and put them together, and I will now show you how to do that type of thing. So suppose we have two charges. Let's say we've got here, you got charge there, positive charge there. Let's say we have a negative charge over there, and let's call it Q1, and let's say it's 0.12 coulombs, and we'll say this is Q2. We'll say negative 0.15 coulombs, and we want to know the electric field right there at that point right there. What is the electric field at this location? And let's say this guy over here is 1.6 centimeters away, and over here, let's say that is 3.0 centimeters. Okay, so with the electric field at that location. Well, it's not hard to do. We got two charges. Each one makes an electric field. So just find the electric fields from those charges with the appropriate Q value and the appropriate R value, and then we'll just put them together. So I'm going to start with electric field from number 1 would be KQ1 over radius 1 squared. So that would be the 9 to the 9, 9 to the power of 9, times the Q value of 0.12. And then we'll divide that by the 0.016, don't forget to square it. And we get an electric field of about 4.22 times 10 to the 12 newtons per coulomb. And since this is a positive charge, the electric field would be going out from it. So it'd be going out this way, and at that point, it would be going towards the right. Okay, so now I'm going to do the exact same thing for Q2. The electric field from number 2 would be KQ2 over radius 2 squared. I'm going to do the exact same type of calculation. I got the 9 times 10 to the 9, multiplied by the 0.15 for the Q, and then we'll divide it by the 0.03 squared. And we've got a electric field for that one, which is about 1.50 times 10 to the 12 newtons per coulomb. And for this one, it's a negative charge, so field is drawn going into it. So over here at this location, the field will be going towards the right towards this one. So this one's also going towards the right. Now, one small thing here. I know that my answers are probably right because my powers of 10 are about the same. That's one of the little tricks or whatever that you can use to tell if your answers are probably right or not, if they're around the same power of 10. If one was 12 and one was like 6, I probably screwed up a prefix or something, or forgot to square the denominator or something, something like that. So if all the powers 10 are around the same, you probably are good to go, or at least you're consistent with your mistake. Anyway, so let's take these guys right here. Now I want the electric field at this location. Well, from charge number 1, I got like 4.2 to the right. From charge number 2, I got like 1.5 to the right. So I'm just going to take those two fields and put them together. So my total field at that location would just be the combination of the two, which is going to be like 5.72 times 10 to the 12 newtons per coulomb going towards the right. And that's it. So they are vector quantities, so you got to look at direction and that a little bit, but that is pretty much it. Okay, so let's take the exact same charges. Let's modify the situation a little bit and show you some subtle differences. So I'm going to get rid of this part right here. Get rid of that. Delete that. And what I'm going to do is I'm going to take that charge and I am going to make it positive instead of negative and do the exact same type of question. Now, I didn't change anything about E number 1, so there's no difference there. For now, what I've done is I've made this charge positive, same amount of charge, same radius. So the actual quantity for the electric field wouldn't change. The only difference is now the electric field would be going to the right because it would go away from this one in that direction. So now instead of that field going to the right, it's going to go into the left. So I'm still just going to do the exact same thing I did before. I'm going to put the two fields together, except instead of adding the two fields, I'm going to subtract the two fields, and that's the only difference. So instead of adding the 4.2 and the 1.5, I got to subtract the two. Looks like E1 is winning, and we'd have a net field of 2.72 to the 12 newtons per coulomb, and there's more going to the right, so the total electric field would be going towards the right. And that's the only difference right there. Okay, so that's sort of how that works. All right, so all you have to do is find the E's and then just ask yourself, is the field going to go left or is the field going to go right? And then just piece it together. Okay, well, let's change this one more time. I'm going to get rid of this again. Get rid of that. Also going to get rid of this as well. Get rid of that there. Get rid of this. And we're just going to change the question a little bit. What I'm going to do is I'm going to take this charge over here, and I'm going to move it beneath instead. And the 3 centimeters would now be there. Okay. So all I've done is I've changed the orientation of it a little bit. I've kept the same radii, I've kept the same charges. That's all the same. There's no difference there. I'm just changing the orientation. So now what we have is what we had before for charge number 1. This didn't change at all. Charge number 1 didn't change at all. The electric field would still be 4.22 times 10 to the 12 newtons per coulomb, and that field would be going out towards the right. So that field is to the right. Now, since I moved Q2 beneath that point, that field would now be going up because it would go from the positive, it would go out this way and keep on going up. So that field right there is now going up. So I got a field to the right and I've got a field going up. So I still have to put those two fields together. I just need to put them together as vectors because they are vector quantities. So from Q number 1, I've got 4.22 to the right, and I'm just going to drop the times 10 to the 12 for now. I can do that. And this one is going 1.5 going up, so my field would be going like this. So I'll just do, basic Pythagoras and find out what the hypotenuse is for that guy. And the hypotenuse would be approximately 4.5. And then I'll just incorporate that times 10 to the 12 newtons per coulomb back, something like this. Of course, I don't also need the angle, so we'll do the tan, so we'll do the 1.5 divided by the 4.22, and we will then take the inverse tan of that to find out the angle, and the angle in there is around 20 degrees. So the electric field at this location would be, 4.5 times 10 to the 12 newtons per coulomb at 20 degrees, and that would be the electric field right there. So again, it's just about find the electric field from one, find the electric field from the other, and then just put them together. Are they going left, right? You add, you subtract. Are they making an angle or something like that? And then just piece it together that way. So this is the type of thing that we'll be practicing with next.